All right, let's dive into it. So maybe we can get through it all. So just remember, what is a rational expression or a rational function? So this is what we were graphing in the last two sections in 8.2 and 8.3 when we have a polynomial on the top and a polynomial on the bottom, and we're dividing each other. These are still functions because a rational function by definition means it's a ratio. So it's a ratio of one thing to the other. So for example, number 1 is a rational function because we have a polynomial on the top and a polynomial on the bottom. We're dividing by each other, and that's just what we call it. All right. So just to kind of review, if I was to graph number 1, right? If I was to graph number 1, hey, Otto. Well, let me do this. This is review from Monday, so always good to get a little refresher. If I was to graph number 1, I would know a couple things about this. So this is reviewing 8.3 while we start 8.4, okay? So what I know about this is if I want to think about the domain, right? So I'm doing a little 8.3 review. If I'm looking at the domain is controlled by the denominator, right? So it is when the denominator equals 0 that we have our asymptotes. So I want to know, when does the denominator equal 0? Well, it equals 0 when x equals -1. Sorry, that's a -1. Let me fix that. X equals -1 and x equals -3. You see that? If you put in -1, you get -1 plus +1, so that's 0 times, it doesn't really matter, equals 0. And then if you put in -3, you get -3 plus 3, which is 0. 0 times something is 0. So those are our two asymptotes of our vertical asymptotes. X cannot basically equal those two numbers, right? And then our horizontal asymptotes had to do with the order of the equation. So which one is bigger, the bottom or the top? So in this case, the denominator is bigger, right? So that means that, hold on. I'm having a brain glitch for a second. So that means that, I believe that means that there isn't a horizontal one, but I don't have that in front of me. So let's go ahead and graph this and see what it looks like. And I could be wrong about the second one. So Desmos, pop it open. We have 2x plus 1 divided by x plus 1 times x plus 3. Okay, I can take off my parentheses here. There we go. All right, so I was wrong. There is a horizontal asymptote, right? And the horizontal asymptote is at 0. That's because the lower number is bigger. So it's x over x squared. All right, so remember when I just did my problem here, right? I said that we would have vertical asymptotes, so up and down spots. X is not going to be able to equal -3. Okay, and that's pretty clear on this graph, right? Looks like we get closer and closer to -3, and over here we get closer and closer to -3, but we never quite reach -3. So there's definitely a vertical asymptote right here. But then you might say, but Mrs. Ross, what about the other one that we said, which was -1? So this is going to be kind of tricky, but let's see if the Desmos will let me do it. Oh, there we go. So see here on my graph where I have -1. At -1, my value is undefined. So I actually have, if you zoom in, let's see if it'll show you here. It doesn't actually show you. Well, that's a bummer. Well, right here in my graph, I have a hole where it's not actually true. There's no value for right there. So that also is not a value. At -1, this function is also undefined. Okay. So everybody remember vaguely kind of graphing these and then looking at the asymptotes and where they're at? And now we're going to talk about why do I have a big vertical asymptote at -3, but I have a hole at -1. Does anybody have a guess just looking at the equation why that would be? All right, so let's look at this rational function. We just kind of graphed it and jumped right in without doing anything, right? But let's look at this rational function. So this is, well, let me ask you a question. If I had 3 times x over, I don't know, over x, are you allowed to cancel the x's out? If I have 3 times x over x, are you allowed to cancel these x's out? Yes. Yeah, I'm going to assume you guys are all saying yes. Yes. Yeah, I got a yes. Yes, you're allowed to cancel them out, right? Whenever you have a fraction and you have a times b over c times b, okay, as long as you have multiplication going on, you are allowed to cancel out like terms. You're allowed to do that, right? That's a rule that we've had for a long time. All right. But when I look to number 1, I see plus signs in there, right? Well, let me go back to this. If I had a plus b over c plus b, can I cancel those out? No, you can't cancel these b's out, right? You're not allowed to do that. You can't do that because it's plus instead of multiply. So you're only allowed to do the canceling out when you multiply. Now let's kind of take this rule of only able to cross out when you can multiply because it gets a little bit confusing when you get to a problem like number 1, right? But if you think about this, I have 2 times x plus 1, which is all in parentheses, over x plus 1, which is all in parentheses, times x plus 3. So even though I have addition in my rational function, I'm still multiplying. I'm multiplying 2 times the stuff in this parenthesis, and the bottom I'm multiplying this parenthesis times this parenthesis. So you can think of that parenthesis as a whole unit. So if you can get whatever is in the parenthesis to match up with the numerator and the denominator, you are also allowed to cancel out the top and the bottom. Okay, so when I do that, my function becomes, so we're simplifying a rational function is what we're doing. So if I do cancel them out, then my function becomes, what color do I want? Purple. 2 divided by x plus 3. 2 divided by x plus 3. Okay, so this is my simplified rational function. And watch this. When I graph 2 plus x plus 3, 2 divided by x plus 3, I get the same exact function that I had before. All right, this red one, the blue one goes right on top of it. The one caveat, though, is that in your blue function, remember in my red function where -1 was, I had a hole. Okay. -1, where are you at? In the blue function, I have a value for 1. Okay, so what happens in these rational functions, if you want to graph using a rational function, is that if you cancel something out, like in this case, we canceled out, this is correct, that's simplified, right? But we canceled out an x plus 1. When you cancel something out, that does not become an asymptote, that becomes something else. We call this a hole in our equation. Okay, so that x plus 1 is no longer asymptote, it's a hole. So when we graph it, we would have to put a hole where that would be. Okay? Does that sort of kind of make sense? And we'll do more examples. This is all we're going to be doing today is simplifying rational expressions. Okay, let's look at number 2. Number 2 is actually easier. So let's look at number 2. 2 is 40x plus 20 over 10x plus 30. So let's simplify this rational function. So when you're simplifying a rational function like this, is there anything that I can take out in the form that it's written in right now? Nope, you can't do anything, right? There we go. Anton says divide by 10. So you can't, the way this is written, you can't cancel out because we technically don't have anything multiplied in the top or the bottom, right? But Anton's right. If I pull out a 10, everything has a 10 in it, right? Oops, there we go. That's what I want to do. Sorry for the weird square. So if I pull a 10 out of everything in here, I'm left with 10 times 4x plus 2 over 10 times x plus 3. So if I rewrite my rational expression like this, then all of a sudden I do have a multiplication in there, right? I have 10 times something in the parenthesis divided by 10 times something in the parenthesis. So because I have multiplication now I'm allowed to cancel out my 10s. And so I can rewrite this as 4x plus 2 over x plus 3. Okay, so these are equivalent expressions. They equal each other. We canceled out a 10. So because we canceled out a 10, that doesn't really give us any kind of hole to our equation. So we're good. So whenever you want to cancel out, make sure that you're canceling out something that's multiplied, not adding together. Now that I have this, could I cancel out this x and x? No, I can't do that, right? Because I'm back to adding. If I could factor something else out, I might be able to. But in this case, you could factor a 2, but it's not going to really help you. When you graph it, these two graphs should be equivalent, right? Because we're just simplifying a rational expression. So 40x plus 20 divided by, see, you have to be careful when you put these in. You need this whole thing divided by 10x plus 30. Okay, that should be the same as 4x plus 2. Nope. If I can type plus 2 divided by x plus 3. So if you do your simplification right, your two expressions should be equivalent when you graph them. Okay. All right, what about number 3? Number 3. So we have 4 divided by x times x plus 2. Can you simplify that at all? So this one's tricky because guess what? You can't simplify it. All right. There's a 4 in the numerator, so there's really nothing that we can factor out in order to simplify the denominator. So sometimes you do get one that you can't simplify. Okay. So let's move on to some more. That's what you're hoping to do, right? Let's look at number 5, 4 and 5. Okay, so number 4, we in the numerator we have x plus 4, and the denominator we have x squared minus 16. So it seems like you should be able to cancel something out when you first see number 4, right? You're like, I feel like I should. But are you allowed to, cancel this x and take this down to x? No, don't do that, right? Can't do that because it's x plus 4 and x squared minus 16. So I don't have anything that I'm multiplying by. I have to have something I'm multiplying by in order to simplify my expression. Okay? So what can I do when I have an x squared? What technique did you learn back in Algebra 1? And we reviewed it in Algebra 2. When you have a quadratic equation, and this is a special kind of quadratic equation, what technique can you use to simplify it? So could we possibly factor x squared minus 16 and make it something times something? Right? We could make this x times x, and then I have 16, which I could do 4 and 4, and I need it to be negative, so if I make one negative and one positive, I can factor x squared minus 16. Okay, so then if you FOIL it back together, you get x squared minus 4x plus 4x, so they cancel each other out, minus 16. So that all kind of works, right? All right, so if I rewrite this as x plus 4 over x minus 4 times x plus 4, all right, I'll draw a line here, see there. Then can I cancel something out? So you're like, well, I have two things multiplied together in the bottom. I don't have anything multiplied in the top. But in your head, you could kind of think of this as this times 1, right? We're allowed to do that. That's all right. So if I do that, then I'm like, cool. X plus 4 and x plus 4 cancel each other out. And I'm left with 1 over x minus 4. Okay, so at the very basic, when I graph this and I graph this, they should look the same. If I did my simplification right, if I simplify my expression the same. So let's do that first, okay? Let's just make sure that we did our simplification right. So we've got x plus 4 divided by x squared minus 16. okay? And then I have 1 divided by x minus 4. Oh, good. So my two graphs look the same. So I did something right, right? Oh, cool. That kind of makes it a darker color. Black, red. I didn't know it did that. See how the colors kind of mix together? All right, so they do match up, so I'm good. Okay. Now let's talk about number 4, and let's talk about the domain and the range, right? So the domain depends on the denominator, right? Here is my denominator of my original. Here's my denominator of my new one. So the new domain is going to control your asymptotes. So when x minus 4 equals 0, that's going to be an asymptote, right? And so that means when x equals 4, we're going to have a vertical asymptote at x equals 4. Okay, so if I go back to my graph, right, at x equals 4, right here, I have a vertical asymptote. So that's cool, right? The new part is, what did I cancel out? I canceled out an x plus 4. I canceled that out. And so since I canceled that out, this is where I'm going to get a hole for my original equation. So I should have a hole at x equals negative 4. Doesn't mean that I'm going to have an asymptote there, but I'm going to have a hole there. So if I go back again to my original equation, okay, and I go to x equals negative 4, let's see if it lets me do it here. Oh, there we go. At x equals negative 4, I don't even know if you can see on here, Desmos does it. It puts an open circle. So that's how you would graph that. You do your whole graph, and then you put an open circle right there. At negative 4, it's undefined because we canceled it out. It's not a true asymptote. It's just the hole in my graph. Okay. And then, so that's my domain. My range, the denominator, the x squared is bigger than x, so the denominator is bigger than the numerator. So my asymptote is at y equals 0, which is right here. So remember, when the denominator, the order of the denominator is bigger than the order of the numerator, then you get an asymptote at y equals 0. Okay, is this making sense? Sorta, kinda. Cool. All right, so let's look at number 5. Let me just, number 5 looks fun, right? Okay, number 5 is x squared minus 2x minus 3 divided by x squared minus x minus 6. So, can we cancel out? It would be so nice if we could just go in here and say, oh, oops, not that. We could go in here and say, oh, there's an x squared and an x squared, and there's a 3, and this becomes a 2, and these cancel out, and there's a negative 2 over 2, and it's negative 1. Don't do that. I've had people do that before. Don't do that. Can't do it. There's nothing multiplying, so you can't cross out. Right now, we're just dealing with a bunch of subtraction, right? Nothing we can do is use our awesome factoring skills back from Algebra 1 to see if we can make this into something multiplying. Okay, so let's try to factor the top, right? We know it's x squared, so it's going to be x times x. And then in order to get a -3, I know I need 3 times 1. 1 has to be positive and 1 has to be negative. Do you remember just looking at this, which one has to be the negative one? Does 3 have to be the negative, or does 1 have to be the negative? So 3 has to be negative so that when I FOIL, right, I get -3x plus positive 1x, which gives me -2x. You guys remember doing that? Okay. So then on my bottom, I'm really hoping that one of my factors is the same. Okay. So I have x times x, and now on my bottom I have -6. And then I need to make those add together to give me a -1. So if I do -3 times +2, then I'm going to get a -x, right? I'll get -6 for the end. And because it's a math book, I'm pretty sure that those are going to work out pretty nice for me anyway, right? So once I've done this, am I allowed to cancel out now? Yeah, right? I can cancel now because now I have multiplication. Now I'm allowed to cancel out x minus 3 and x minus 3. And my expression is now x plus 1 over x plus 2. Okay. So if I graph the original and the new, I should get the same graph, right? That's my first check. So you should all get these right on your test because you can check it, right? Check and see if it's right. X squared minus 2x minus 3 divided by x squared minus x minus 6. Okay, that's my original. And my new equation is x plus 1 over x plus 2. X plus 1 divided by x plus 2. Okay, so let's see. There's my blue. I turn the black on, and it turns it like a Columbia blue, and there's the black one, and they match up with each other, right? Okay, if I look at my new equation, the horizontal asymptote is when the denominator equals 0. So when x equals -2, -2 plus 2 is 0. So I have a vertical asymptote at -2. Okay. Also, if I go to my black graph, I canceled out an x minus 3. Right? I canceled out an x minus 3. So when that equals 0, I'm going to have a hole. So when x equals 3 on my original graph, I'm going to have a hole in my graph. So if I go to the black graph only, and I go to x equals 3, nope, I skipped it. There we go. I have a hole right there because that's what I canceled out, right? And the last thing is my horizontal asymptote. So this expression and this one, in number 4, remember the denominator was bigger. X squared was bigger on the denominator than x. So that meant that my horizontal asymptote was y equals 0. In number 5, they're equal to each other. I have an x over an x. So then I just look at the number out front, which happens to be a 1 over a 1. So my vertical asymptote, horizontal, I always want to say that wrong. My horizontal asymptote is at y equals 1 because I get that from 1 divided by 1. So again, if you go back to your graph, you can see that there is a horizontal asymptote at y equals 1, right? So we have vertical asymptote at x equals -2 and y equals 1. And then Anton taught me this. I can make them dashed so they look like asymptotes. There we go. I don't know why the purple one's bigger than the green one, but you know. Oh, there we go. So there's your two asymptotes, and then you have a hole right there at 3. Okay. Everybody hanging in there? Good. All right. Last few. Actually, number 6, I think I like better. Number 6 might be my favorite problem that we're going to do. Guess why? So look at number 6. Okay. There is a bunch of numbers and a bunch of variables. Is there any addition and subtraction in there? No, right? This is just a huge multiplication and division problem. So number 6, when you see number 6, you can just go for it. There's no addition and subtraction. Everything's multiplication and division. So crossing off in numerator and denominator is fair game. Okay. There's a couple techniques how you can do this. You could just start like this is and cross everything off. You could also multiply the numerator. So we have 3 times 6 is 18. We have 3 times 6. We got x to the 5th times x, which is x to the 6th. And we have y squared times y squared, so y to the 4th. Okay. And the denominator, we have 8 times 9, which is 72. X times x cubed, which is x to the 4th. And y times y, which is y squared. So one option is you can multiply the numerator and the denominator, and then you can cross off, right? 18 goes into 72. 3. How many times? I don't think it goes in evenly, does it? Oh, it does. 4. 18 goes into 72 4. Oh, thanks, Anton. 4 times, right? X to the 4th and x to the 6th, this becomes x squared. Okay. And y to the 4th over y squared, this just becomes y squared. So when you write this all out, you end up with x squared, y squared over 4. My favorite kind of problem, right? You also could have, if you wanted, before you even multiplied across, you could cross things off. So there's an x down here and an x up here. You can cross those guys off. There is a y and a y and a y squared. We can cross those off. We have 3 and 9 makes 3. And then 3 and 6, this becomes 2. And then 2 and 8, this becomes 4, right? And then we have x cubed and x to the 4th, so this becomes x squared. So if I do all that, if you followed that, I get x squared, y squared over 4. Okay, if you didn't follow this green, that's okay. Some people are super comfortable with like crossing things off right in the problem. Some people, you want to do that step in between to simplify it. But either way, any way you simplify it, you're allowed to do it. You can multiply it first and then cross off. You could cross off with just within the fraction. Lots of different options for that one. Okay. Everybody all right with that? Cool. All right, two more. Two more we're going to do. So we might wrap up early today. Number 7 and number 8. Let's do number 7. All right, back to put addition and subtraction back in there. Yuck, right? Now we can't just cross off like number 6. That one was so fun. So what we're going to have to do is look at it. Is there anything we can cross off right now? Again, I would have a lot of people tempted before to cross these two off, which you cannot do because 2x squared is being subtracted by 10x. So if this 10x was gone, you're fair game, cross those off. But since you're subtracting by a value, you can't do it. Okay, so what you're going to want to do is we're going to try to work every part of our fraction and see if we can make it a multiplication problem. So let's just look at the numerator of the first fraction. Okay, the numerator of the first fraction is 10x squared, or 2x squared minus 10x. Okay, so what I notice about that is they have some terms in common. They both have a 2 and an x. I look at the greatest common factor of both of them. So I can factor out a 2x of both of those, and I'm left with x minus 5. So you see that? I pulled out of both of these 2x, and I'm left with x minus 5. So hopefully that helps me out, right? We'll see. Okay, so now I'm going to work on the denominator of my first fraction. So my denominator is x squared minus 25. So hopefully you know that pattern for that, right? And that is x minus 5 times x plus 5. Right? That way the minus 5x and the plus 5x cancel each other out, and we're simplified there. Okay? Now multiply. This is a multiply there, so that's good. X plus 3, I'm going to just write it like this so I know in my head that that's all together as one quantity. And then in the that's my numerator of my second, and the denominator of my second is x squared, 2x squared. Okay, so now what I have is a rainbow of numbers, but now what I have is a multiplication problem, right? So now I am allowed to cancel out my x minus 5 and my x minus 5. I'm allowed to do that, right? Because I'm multiplying all these quantities together. I'm allowed to cancel my 2 and my 2 because those are being multiplied. They're not being added to anything, right? I can also cancel my x and my x squared, and this can just become x in the denominator. And I think that's all I can cancel. So I'm left with x plus 3 in the numerator, okay? And then I have x times x plus 5, x times x plus 5 in the denominator. So these two expressions are equivalent to each other. And if you pop them into Desmos, you'll get the same graph out. Okay. Like I said, I think these are kind of fun. I don't know if you guys are like, fun? Not exactly my idea of fun, right? All right, so number 8 is our last one. This is the first one we've done like this. What happens if you have division? Who remembers the rule? If you're dividing by a fraction, what do you do? So remember, back in your day, if you had A over B divided by C over D, if you're dividing by a fraction, what you do is you get to change it to multiplication by flipping the numerator and the denominator. Remember doing that? Sorta? Okay. So then what do you think you're going to do when you have a big, crazy polynomial like this and you're dividing? You're going to do the same thing, right? You're just going to rewrite this as multiplication. So you have 4x and you have 5x minus 20. And instead of dividing, we're going to make it multiplication. And we're going to flip the numerator and denominator. So x squared minus 6x plus 8 goes on the top. And x squared minus 2x goes on the bottom. And now we're multiplying. Okay. Can I cancel anything out yet? Boo, no. Right? Can't cancel anything out. So let's look at each piece and see if we can simplify it. So we got 4x in the numerator of the first. Can't really do anything with that. 4x just kind of hang out. Okay. In the denominator, we have 5x minus 20. So those have a like term. They both have a 5 in it. So we could take that out, right? We can have 5 times x minus 4. Maybe that'll help us out. We'll see. Okay. We're going to multiply. We're going to look at the numerator of our second fraction. So we have x squared minus 6x plus 8. Okay. So since we have a positive 8, well, we know it's x times x. Since we have a positive 8 and a negative 6, we're probably going to have a negative times a negative. And why don't we do negative 4 times negative 2, because that'll give us positive 8, but it also gave us negative 6 when we add them together. And then last up, we have x squared minus 2x. So that one, we can pull an x out of both of those and get x times x minus 2. Okay, now is the fun part. This is the part I like. Now we have a giant multiplication problem, right? I know we have some parentheses. We have, well, it's all subtraction. We have a bunch of subtraction in there, but it's all being multiplied in parentheses. So we're okay to cross off, right? So we have x minus 4 and x minus 4. And we have x minus 2 and x minus 2. And we have an x and an x. So if you simplify this whole thing, you actually are left with 4/5. So this big fancy expression always equals 4/5, which is kind of crazy, but sometimes it works like that. So if you would have typed that in Desmos, I think it would have just given you 4/5. Let's see. We have 4x divided by 5x minus 20. Okay. I don't even know if I can do divided. Yeah, I'm just going to go ahead and multiply just to make sure that we get it in there right. And the top is x squared minus 6x plus 8 divided by x squared minus 2x. And I think I put an extra little thing in there. Oh, okay. Oh, undo that. There we go. All right, so if you see on your graph here, the answer is the y equals 0.8, which is 4/5. It always just equals 4/5. I thought maybe it would tell us the answer, but it's always 4/5. Okay. So I think it's kind of fun. If you don't think it's fun, it's okay. But I like the part where you get to cross things off. I think that's cool. Um, so try that out, guys. We're just going to keep working through chapter 8. So that's kind of where we're at. I think I've got everybody's chapter 7 stuff. I should be grading that in the next day or two. So I will let you know. All right, guys, have a good rest of your day. I'll see you on Monday. Bye. Thanks, guys. Bye.